welcome to CPE 329 Analog to Digital Conversion lecture. Today there's two kind of a review learning objective is to review sampling theory, which you should have covered in EE 228, and then also we're going to talk about how analog to digital converters are how they work and also how they're built. So in general though, so the sampling theorem stuff is going to build into analog to digital converters, and an analog to digital conversion, what happens is that an analog voltage gets translated to an n-bit digital representation of that voltage. And we'll see some examples of that. Okay, so first some review material. If you have a band-limited signal here between where S is equal to 2 pi over T, T is going to be the sampling frequency, and we need to make sure that we have we've met this restriction basically for sampling here. So we have to sample at least what they call the Nyquist frequency, or twice the highest frequency of the sampling signal. So kind of a time domain representation of this. If we have the sine wave and we only sample at the frequency of the sine wave here, we won't be able to reconstruct the sine wave here, as shown by the top red line up here. However, if we sample at least twice the frequency, then we can actually reconstruct the sine wave. So that's the review session there for Nyquist sampling. So analog to digital converters, at the simplest, we're going to need a circuit called a sample and hold. The sample and hold circuit is really just an analog switch with a capacitor, and the capacitor charges and discharges to the input voltage. And we need to make sure that the analog switch operates at the sample rate. So that's a one restriction on analog to digital conversions, is how fast you can do it. And also, we're going to talk about how many bits they sample as well. And then, so the amplitude of each sample is going to be held constant during the conversion process, and so that's what the sample and hold circuit accomplishes for us. The sample and hold circuit is pretty simple. It looks like this. There's a analog input, and here's our sampled output here, and so the switch will periodically close and charge up this capacitor. So if we look in time domain, when we're going to use the sampling clock here to control the FET here, and when the sampling clock is high, the FET's closed, and our sampled voltage will rise on the capacitor, and then we'll open up the FET and it will keep its charge, and so on and so forth. So this way we can get we have steady inputs for our analog to digital conversion process. And so now if we think about just using an analog comparator, just an op-amp here, we actually have a 1-bit analog to digital converter if we just if we have a pull-up on the output here of the comparator. So basically we're going to generate either a low input or a low output or a high output here on this using this comparator. And so you can figure, well, okay, if we create a whole bunch of different reference voltages here, this would be like 0 volts, and this is going to be 1 volt step up, and so the voltage step here is going to depend. The size of the step is going to be determined by the dynamic range that you want. How much? What's the maximum voltage that signal you want to convert? And also by the number of bits here. So we have 2 to the n minus 1. That's where n is the number of bits that's going to be created from our circuit here. So typically, if this is, let's say 5 volt, you wanted to convert a 0 to 5 volt signal, the 0 volt would show up here on this comparator, and something like 5 volts would show up towards this. It'd actually be a little bit less than that. And so this this comparator would be would be active. And then everything in the middle here, if we linearly distribute 0, 1, 2, up to 2 to the n minus 1 v steps, then we can create a nice linear mapping of analog to digital here using this priority encoder. The priority encoder, it's just what it does is so only one of these comparators is going to be on, and what it's going to do is it's going to create a binary vector. So if this is the V step here, if this is the highest voltage here, and this is a, let's say, 10-bit where n equals 10, then this will be a 1 up here, and everything else will, then this will be a 1, this will all be zeros down here, and what the priority encoder will do is make this all 1s on the output, indicating that's the highest value. So it's basically a single bit to binary converter. So combinational A to Ds like this, they are used. They are and they have the fastest conversion time because everything happens in parallel, but they're pretty expensive to make, and so they're used sparingly because they require lots of comparators. So the alternative is to use a sequential thing where you have, okay, here's an op amp here, and we're going to use we're gonna look at the output here, and we're going to feed back some reference voltage, and so this will take many passes here before we settle on the analog the detecting what the analog signal should be. So this is also could be used, but not very many people use this. Instead of doing an all parallel version here, going back one slide to the combinational A to D, or all serial here using a single comparator. What we typically see in most analog to digital low-cost chips is that we use a single comparator here, and we're going to run essentially a binary search through the voltages rather than just to keep incrementing or decrementing until we find the right value. So this comparator here. Here's the sample and hold circuits, the input here, holding the voltage in here, and here's going to be our reference voltage. And we're going to put it in here, and then we're going to make a guess, basically, using some circuit here, controlling a digital analog converter and providing a new voltage here. And we're going to jump back and forth until we have until we hit the right point, until the comparator tells us yes, we're right. So basically, this binary search in software will allow us to take use n loops through here to search to n different possible results. And so this is the most common type thing for analog to digital conversion.